In looking for a many-path formulation of quantum field theory, we wrote an amplitude of probability, Z, for the field to evolve from vacuum to vacuum over an infinite time. The physical laws and the physical properties of the system enter through the Lagrangian. In particular, this Lagrangian encodes Lorentz invariance, space and time translational invariance, rotational invariance, etc. In other words, it contains all the symmetries of the system. So nothing is expected to happen to this system, in particular if the vacuum is an eigenstate of the Hamiltonian. During the evolution, the system will therefore remain in the vacuum, and nothing interesting will be extracted from this quantity. So we will do what we have always done, whether it was in quantum mechanics or even in classical physics. We will break symmetries. For instance, take an object of mass m that obeys a Hamiltonian which is time and space translational invariant. We know that in classical mechanics such object will have a uniform motion, and in quantum mechanics its wave function will be the one of a spreading wave packet. But things become more interesting when we start breaking symmetry. So for instance, break translational invariance by putting the object at the end of a pendulum in a gravitational field. But if we do nothing to the pendulum, it will not move, it will remain at rest. If I want to probe the behavior, the properties of the pendulum, I will need to also break time translational invariance, for instance by giving it a kick at the initial time. In doing so, the pendulum will enter into motion, and I will be able to observe its oscillatory behavior, calculate or measure its frequency, etc. So the idea is to do the same to our path integral. We will keep the Lagrangian as the object which encodes all the physical laws, the physical properties of the system, the symmetries. And to probe these properties of the system, we will add to the Lagrangian a term which explicitly breaks symmetries, and in particular it will explicitly break space and or time translational invariance. But this is not enough, because in just adding the function j of x and integrating over space and time, we only add a constant to the action. And we know, for instance, in classical physics that because we require the action to be stationary, adding a constant will not change anything. So we need to add not only j of x, but also a function of the field. We will take the simplest function possible, which is just a linear function in phi. This function of space and time j is called a source. Sources are here to perturb the system and to probe its response. Therefore, the sources are the choice of the physicist. For instance, we may have a theory which will describe the electrons and their interaction via the exchange of photons, that's quantum electrodynamics, and that will be defined by the Lagrangian. And then when I want to look at a physical property of a system, for instance the decay of a particle like the muon, or the scattering of two electrons, or the pair creation of an electron and a positron, etc., that will be done by choosing adequately the source. So the choice of the source is extremely important. Tell me how you choose your source, and I will tell you if you are a good physicist. In fact, sources are so important that Schwinger, one of the founders of quantum field theory, said he was doing sorcery.